and technical solutions, before they become just very, very difficult. So thank you again for the invitation. I happen to know that the development of parity violating electron scattering, I started working in the mid-'80s, but I know that Willy followed very closely the development of this field as he was also involved in the PP parity violation experiments. Okay, so I'm going to start with an introduction, and that's really the main message that I want to be able to essentially communicate to you. So hopefully that will only take 15 minutes, but if it takes longer, that's fine. And then I do want to spend some time, because this is very recent news, 2 new experimental results over the past year and a half. I want to talk about P-Rex and C-Rex. And then finally, if I have time, I'll wait till he's finished with that. Yeah? Is that good? If I have time, I will talk a little bit about a new experiment called Molar that's keeping us quite busy right now, getting ready over the next couple of years. Okay, so let me just start. And the story begins for parity violating electron scattering back in 1958. There was a brilliant paper by Zeldovich. And in that paper, he asked, is electron scattering parity violating? And why would he ask that question? So let's start with the discovery of parity violation, which was by Madame Wu, watching the decay of cobalt-60 nuclei in a magnetic field. And as soon as she saw that the betas came out not isotropic, anisotropic, she went up one floor and declared it to TD Lee that parity is violated. Now, let's just make sure that we understand why that is so. So the B field vector, which is shown here, and the spin vector in cyan are axial vectors. So when you reflect, they don't change direction. But the momentum vectors in red and blue do change direction. And so in mirror reflection, this phenomenon becomes this. And if this is not observed, then you have parity violation, and which is essentially what you see here. So here's what Zeldovich asked. So as you know, Feynman and Gelman proposed the V-A theory for parity violation. And then Zeldovich asked this brilliant question. He asked, if this amplitude exists and it's parity violating, maybe we should look for this amplitude and electron-proton weak scattering. And then he made the astute observation that, in fact, this would interfere with electromagnetic scattering. And therefore, you would have an interference term. And maybe that could be observed, and it would be parity violating. So he proposed in this brilliant 1.5-page paper, this observable, which people who do PP scattering experiments are familiar with, as you heard from Thomas Roser yesterday. The parity violating asymmetry, you bring in a longitudinally polarized beam on an unpolarized target, and you look at this fractional difference in the cross section. And if that is non-zero, that's parity violation. And then he went on in this 1.5-page paper to actually estimate what the size of that would be. Because the electromagnetic amplitude goes like alpha over q squared, you get G Fermi q squared over alpha. And so this would be about 10 to the minus 4 times q squared and GeV squared. And he made an estimate of that. So let's convince ourselves that this is indeed parity violating. So I do the same exercise here. I bring in a longitudinally polarized beam in the center of mass frame. I do a reflection. The spin vector doesn't flip sign. I do a trivial rotation. And if you compare this to this, the only thing that's changed is the longitudinal polarization of the electron beam. So you polarize the beam coming in. You have an unpolarized target. You measure the fractional difference in the cross section. Now, this stayed in everyone's archives for many years because people in those days didn't know how to get a q squared of 1 GeV squared. And so, and also, they didn't know how to get polarized electron beams of enough intensity. So this stayed around for a while. People didn't discuss it very much. But the theorists were busy in the meantime. In the 60s, we came up with the Glashow-Weinberg-Salam model, and Weinberg incorporated the neutral current. Here is the V minus A charge current, and then he introduced the weak mixing angle. And so now we have the neutral current with different couplings for the right and left-handed particles. And in fact, the first neutral current observation was made in the early 70s. But in fact, in the mid 70s, there was a question whether Weinberg had it right. Because for this assignment, the right-handed electron is in an weak iso singlet. But in fact, if there's a weak iso doublet with a heavy neutrino, in fact, it turns out that this amplitude goes to 0. So this became a pressing question. In fact, there is no way they could have won the Nobel Prize without answering this question. And in fact, the first atomic parity violation experiments were negative. But then in the mid 70s, this experiment, SLAC E122, was done, where they were able to show that parity is indeed violated in weak neutral current interactions, in electron quark interactions. And then the weak mixing angle that they measured was the same as inferred from neutrino scattering in the bubble chamber. So I want to talk to you about that experimental technique. It was a massive leap in technology. And the primary reason was, just like as Thomas Roser mentioned, you had to have well over megahertz rates, and you needed to keep the beam properties unchanged under helicity reversal. And the big innovation was the invention of the gallium arsenide photocathode as a source of the polarized electrons. So you bring in a circularly polarized light onto gallium arsenide cleaved in just the right way. It turns out that the valence band and the conduction band have quantum numbers such that the circular polarization of the light determines whether the electrons that come out are longitudinally polarized one way or the other. And now it's a trivial thing of having to put that into a polarized source, have a large potential difference, and then you can inject polarized electrons in an accelerator. There is a lot of black magic that happens both in the generation of the photocathode as well as what you have to do to manipulate the laser light that I won't have any time to go into. But it allowed the fact that you could have rapid polarization slips and that you could keep the beam unchanged under helicity reversal. So in fact, the other big innovation was what we call flux integration, which Thomas also mentioned briefly yesterday. And basically, the idea is that the weak interaction signal is buried in the known background of the electromagnetic interaction. And it's really like the entire accelerator is a lock-in amplifier. So very large lock-in amplifier, but essentially that's what you're doing. And in that sense, it is quite similar to the experiments that were carried out in PP scattering, and in particular, the Willy-Haeberli experiment that was mentioned by Thomas yesterday. So here I compare the two. You can see here that the similarities are the flux integration technique. You can see here, you could just convert 50 hertz to 60 hertz, and you could just put the same cartoon here over here. Essentially, this is the electron cartoon from this paper here, seminal paper, and this is the PP scattering cartoon from these papers here. And you can see that the modulation of beam properties, rapid helicity reversal, cancellation of systematics, there are many similarities, but there are some very interesting differences too. Because of the Q squared in the numerator for electron scattering, you have this big sensitivity to the scattering angle in the analyzing power, which is not the case for PP scattering. And then the preparation of the polarization states is fundamentally different. And then there is, in PP scattering, you have this polarization profile sensitivity that is really absent in electron scattering. So now I'm going to talk to you for the rest of the talk about electron scattering. And essentially, if you look in the larger context, you are looking at semi-leptonic and leptonic weak neutral current interactions very much lower than the Z mass. So there is neutrino scattering, of course, and then there is the weak electromagnetic interference that Zeldovich talked about. There are two ways to get it. One is opposite parity transitions in heavy atoms, so-called atomic parity violation, and then the spin-dependent electron scattering, which is essentially what I'm going to talk about for the rest of this talk. So if I just take the Zeldovich formula, I just have to add actually just this term to whatever Zeldovich originally predicted. You have to have pseudoscalars, so it's the axial electron coupling times the vector coupling of the target plus a kinematic factor times the vector coupling of the electron times the axial coupling of the target. And depending on these values and of the target couplings, you can change the asymmetry from anywhere from 10 to the minus 4 to 10 to the minus 5 times q squared and GeV squared. And what has really flourished in this field is the fact that by measuring what we call the weak charge in the jargon of the field, we are able to push all kinds of different physics. In the early 80s, goal was to show, as in the Prescott experiment, that sine squared theta W was the same as in neutrino scattering. But in the 90s, assuming the standard model, you could probe novel aspects of hadron structure, strange quark form factors, and the neutron RMS radius of a heavy nucleus. I'm going to talk about that a little bit. And then, since the late 90s, we have now realized that precision measurements at carefully chosen kinematics can probe new physics at the multi-TeV scale. So that's the rest of my talk. So let's just start with the standard model tests in the 80s, because those experiments happened at roughly the same time as the PP original pioneering PP experiment. So in particular, it was realized in the mid 70s, this paper by Feinberg in 1975, that elastic scattering of a spin zero isospin zero nucleus like carbon 12, the elastic scattering rate is insensitive to nuclear structure and is a clean probe of sine squared theta W. And this was the MIT Bates parity violation experiment, which was published in early 1990. In parallel, there was an experiment at backward scattering of beryllium-9 at Mainz. And these experiments were the first to kind of measurements of electron nuclear weak interactions. It pushed experimental technology into the part per million level and spawned a new generation of experimenters and experiments. And in particular, it was realized then that to look at it in a model independent way, there are 4 couplings you need to measure because you have up and down quarks. And you also have the fact that you have axial and vector couplings. And so there are 4 couplings that you really need to measure. And so these experiments pushed down to 100 part per billion systematics and hundreds of megahertz of rate. But at that time, the PP scattering measurements were ahead of us, because in those experiments, you were actually down by an order of magnitude in systematics, down to 10 parts per billion, as in the late 80s publications, and also tens of gigahertz of rate. So we had some ways to go, but we've been busy the past few decades. And so here is a summary of many, many electron parity violation experiments. And we like to show it in this kind of graph. This axis is the error in that each of these points is a past or future measurement. They're listed here. This is the error in the measurement, and this is the actual value of the asymmetry. And you can see that starting with the pioneering experiments over here, we've been steadily marching down to the bottom left. And in fact, those of us who work in this field know that marching down the bottom left is not so challenging. What is really challenging is to march down to the bottom right, because what I've drawn here is a 100% measurement, a 10% measurement, a 1% measurement, and a 0.1% measurement. And that is far more challenging. The normalization errors are far more challenging, knowing the analyzing power, knowing the beam polarization, things like that. But getting down to sub-part per billion is the current state of the art. Now, of course, I won't have any time to talk about what I'm sure all of you would be interested in, which is all the technology that had to go into this, which I list here. And there were many parallels to the kind of development that happened in electron and proton scattering experiments. So this is sort of the end of my introduction. And so at this point now, what I'm going to do is give you a sense of the 2 new experiments, PREX and CREX. Why did we do them? What are the results? And then maybe in the last 5 minutes, I'll have time to talk about the molar experiment, which we are doing in the future. Okay, So a brief digression of all the history of the various experiments. One set of experiments we did in the 90s and the early 2000s is looking for strange quark form factors. So this is a one-slide summary of that. The idea was very simple. And given that Steve is going to talk about it, let me just quickly remind you that this is approximate charge symmetry here, not exact charge symmetry. So if you have approximate charge symmetry, and then you use the standard model to go from the photon to the Z boson, it now gives me a way to flavor separate 3 flavors in the nucleon. And so this was why we wanted to measure the parity violating elastic scattering off of the proton. And so by doing that, we were able to get the so-called strange form factors. So there was a series of experiments doing that. And this is kind of the way we like to show the final results from those experiments. What is plotted here is the electric plus a kinematic factor times magnetic form factor of the proton versus q squared. And the green points are the G0 experiment. And then you have the sample, the A4 sample is shown here in the backward angle here, A4 and the HAPEX series at Jefferson Lab, A4 at Mainz. And then you can flavor separate at 3 different q squares. And basically, you can see that the strange quark form factor is very small. This purple line here is the 3% of the electromagnetic form factor. So the conclusion from this program is that we've done sensitive flavor separation at 3 q squared values. The strange quarks are no more than a few % of the electromagnetic structure of the nucleon. And modern lattice QCD calculations are now finally catching up and confirming this experimental situation. All right, so then let me move on to something that's kept us busy over the past 15, 20 years, which is measuring neutron densities with parity violation. So the concept is, again, very simple. It was proposed in the late 80s, early 90s. The idea is that when you scatter do electroweak scattering, you have a situation where you have the electromagnetic form factor for the charge occurring, which I'm calling F sub p here. But then when you do the weak amplitude, you have also the neutron density coming in because of an accident in the standard model where the weak charge of the neutron is much, much larger than the weak charge of the proton because the weak mixing angle is very close to 1/4. Sine squared theta w is very close to 1/4, which is an accident of nature. And therefore, you have 1 here and you have 1 minus 4 sine squared theta w here. So effectively, the parity violating asymmetry, the numerator here is a measurement of the neutron form factor, from which you can infer the neutron RMS radius of a heavy nucleus. So this is a very clean electroweak probe of this quantity. And so in fact, if you measure the asymmetry to 3%, you're able to measure the radius, for example, of lead-208 to 0.07 femtometers and calcium-48 to 0.03 femtometers. And of course, though, these are challenging experiments because you have to dial the q squared down to very small values. And so that's what motivated the P-Rex and C-Rex experiments, the lead radius and the calcium radius experiments. Here is a model calculation, many different model calculations, but you can see that there's a straight linear correlation between the asymmetry versus the neutron skin of lead-208. So by measuring the asymmetry to 3%, you can infer the neutron skin to 0.07 femtometers. So our job is to figure out where we are on this curve. Now, calcium-48 is also important, because there are mean field theory predictions for both the skin of calcium-48 and lead-208, and it's very important to try and measure them because having a lighter nucleus allows you to explore things like 3 neutron forces. So here is a quick rundown of the P-Rex experiment. We ran that in June to September 2019. So the q squared has to be tiny in GeV squared. That brings the asymmetry down to less than a part per million. And our goal was to get to 20 parts per billion. Here is the giant high resolution spectrometers in Hall A at Jefferson Lab. that allows you to do flux integration by separating elastic scattering from lead from the first excited state, which is only 2.8 MeV away. But we're able to separate that because of these magnificent high resolution spectrometers. This is a cartoon of the lock-in amplifier, which is the lab. Everything has to talk to everything else to do a parity violation experiment. So this is a cartoon of what Hall A looks like and what we had to do in there. One of the challenges, I'll just talk about one, which is kind of interesting, which is how to not punch holes in a lead target when you put 70 microamps of electron beam through it. And the way we do that is to use a copper jacket and run cold helium gas through a sandwich, diamond lead sandwich, which is shown here. And then you can see that we weren't quite sure of ourselves. That's why we have so many targets. And in fact, it turned out that in our pilot run, we did punch a couple of holes. So we came back and we had 10 targets. And it turned out there was a technical reason why we needed 6 of the 10 targets, even though we didn't punch any holes. And that's because after about 10 days of running, the diamond turns into graphite and loses all its conductivity. So we found a way to figure that out, and we would move after 10 days to a different target. So we ended up using about 6 of the 10 targets. So that's just one of the many exciting things we did here. Okay, so one of the things which is the exquisite control of the polarized electron beams. So here is shown a cartoon of the polarized source at Jefferson Lab. This is sort of a enormous amount of technical developments that have happened over decades on polarized electron sources. I just remind you again that we can flip the sign of the asymmetry by inserting a half-wave plate into the laser light. So that's one way we flip the sign of the asymmetry to cancel systematics. The other thing we can do is actually manipulate, just like you do in PP experiments, using solenoids, the direction of the spin. And so we ran it in 2 different orientations. We called this is a Wien filter with cross E and B fields. So we did that as well. And then we came up with a new technology for how we make a circularly polarized light that ended up being a pretty major breakthrough in the control of these kinds of electron beams. When you flip the helicity reversal, when you flip the helicity of the beam, for the PREX2 experiment, which we ran in 2019, we were able to get down here. This is in nanometers, the X difference, the Y difference, grand average, nanoradians in angle, and the energy of the beam, part per billion. So we were able to get down to these levels, which is going to be crucial for our next generation of experiments as well. So here is the PREX results. Those of you who do PP parity violation experiments will appreciate this plot here, which is all our data. And there are millions of entries here. And this is essentially, as you flip back and forth, you're doing the experiment millions of times. And you can see this is data. This is not a Monte Carlo. It's perfect Gaussian over 5 orders of magnitude. And we do not cut on this distribution. So there's a little bit of hair left in the 6th order of magnitude. We leave it there. And this is the centroid of this is our final answer. Okay, in the parity violating asymmetry. This is in percent here. But of course, we have these 4 different ways we ran the experiment, and these are the grand averages from that. We blind the asymmetry, and we don't unblind until we are done with everything. And so you can see 5 minutes. Okay, you can see here the agreement. Here is the grand average. Here's another way of looking that we have. We know how we do our statistics. And this is our final answer. And then this is the weak radius of lead. We had a pilot experiment, and then this is our final answer from PREX2. And so this is the grand average neutron skin in femtometers. So what is nice about this experiment is that we are now able to use this information to infer the interior baryon density of lead-208, which is something that is a direct electroweak measurement of this quantity, which is close to the saturation density, as you would expect, of a heavy nucleus. But it's a direct measurement. There's also connections, which I won't have time to go into, to neutron star physics. I want those of you who are not paying attention, there's a small difference between this scale and this scale. And so, but there is quite a similarity there. And if you look at, remember the LIGO result, right when the neutron stars are merging, there is a tidal deformability. The actual neutron star becomes a teardrop shape. And that deals with the tidal deformability, which is affected by the nuclear equation of state. And so there are now models being worked on that try to couple using the nuclear equation of state, the neutron skin of a heavy nucleus to the radius of a neutron star. So I won't have time to talk about this model, but this is an extraordinary connection to neutron star physics. Okay, so we also did I won't go into this, why we motivate a second calcium measurement. I'll just show you the result. Here, calcium was a trivial experiment compared to it because the asymmetry is bigger for calcium for technical reasons. Here is our run, which ran through COVID. So we had breaks, but we managed to come back during COVID and ran and finished the experiment in the summer of 2020. And we have just published right here, and PRL has just accepted our publication. It should show up in press in the next week or two. And the legacy of these experiments ultimately is this plot. What is shown here is the charge minus the weak form factor of calcium-48, charge minus the weak form factor of lead-208. I remind you that if the neutron and proton radii were the same, this would be 0. And so this is our result. And the theorists tell us that the neutron skin of lead-208 is too thick and the calcium-48 skin is too thin. But I tell them that their theories are wrong. And so they have to find a way to get down here because this is nature. You can't complain about that. So that's the observation we are making, and you can expect that in PRL pretty soon. All right, so the final maybe 2 minutes is going back to searching for physics beyond the standard model. And this is now part, thing you're going to hear about EDMs today. The basic idea here is that the standard model Lagrangian can be then expanded to higher order terms to look for new physics. You're looking for vestiges at low energy with these kinds of amplitudes. And the way neutral currents come in is to look for new flavor diagonal neutral currents. And you're choosing quantities that are precisely calculable in the standard model. And you need to reach contact interaction scales of 10 TeV to compete with the colliders. So I won't have time to go into trying to motivate all the 3 different kinds of experiments, which is elastic scattering, deep inelastic scattering, and molar scattering. They're all 3 being pursued. And we like to show the status of the field in a plot like this, which is the weak mixing angle as a function of Q. This is the weak mixing angle. These are the published measurements. There's atomic parity violation, neutrino scattering, slack E158 molar scattering, and then elastic EP scattering, and then deep inelastic scattering. And then these 3 red, molar, P2, and solid, are the future. And they're shown here the error bars that we are targeting and the Q value that we are going to be at. We put this at arbitrary central values, but this shows you the error bar. So let me just flash in the last minute just the fact that we are now working on this beast of a project called Molar. And it's come a long way from being a tabletop experiment. And I am buried in project land at the moment over here. But we do have a very nice design. And we are reaching unprecedented sensitivity in electron-electron scattering, parity violation. And to put that in context, what we are trying to do is accessing discovery space that cannot be reached until the advent of a lepton collider. If people have questions about how I defend this, I can talk to you about it. But this is the main message, is that we are as sensitive as a new lepton collider when we get this measurement done. And so I'll just flash the fact that this is now the technical challenges here. There's a new generation of technical challenges. We are well over 100 gigahertz in rate. We have a 9 gram per centimeter squared, 1.25 meter long liquid hydrogen target. There are many other challenges here that I won't have time to go into. But since I'm out of time, I will just conclude here by just stating that parity violating electron scattering, it has enabled unique studies of the weak force. Technical progress has enabled unprecedented precision. There is a long line of new experiments that we are pursuing now. This is a 4-decade-long productive research program that will continue to flourish for at least another decade. And I want to just end by making a personal comment. Thank you for the invitation to attend this very interesting symposium. And as you can see, a common theme in all the experimental talks is chasing technically challenging innovations with polarized beams and targets in pursuit of fundamental problems. And this is in no small part, not only due to the drive, energy, and technical brilliance, but also the community leadership of Willy. Thank you very much. Yeah.
Thank you very much, Krishna, for a very interesting talk. I'm sure there will be questions. Siv Vigdar.
Krishna, do you know in the early days of the EP parity violation, was there a learning curve back and forth between the PP experiments and the EP experiments in how to handle systematic errors?
Yeah, so I was a very early grad student when these were happening, but essentially, when the transverse polarization issue in PP scattering was being actively debated, there was a flurry of activity in the electron scattering to make sure we didn't have this problem. There could potentially have been that if we had a polarization profile issue, but turns out, so that was one thing where we were alert to this fact and had to check. And then from our side, I think the fact that we were able to make innovations in the electronics, I think some of that went back to the PP scattering experiments as well. So there was a little bit of back and forth in the early days for sure. And even the current round of neutron experiments, for example, there's a lot of like NP to D gamma, things like that. There have been some back and forth as well. Yeah. So.
Krishna, how much of this was Willy really involved in? Where was he really the sort of the conduit for ideas that made all this happen?
So I think in the early days, he was in touch with the group at SLAC, yeah. Which is Charlie Prescott and Charlie Sinclair. And again, I was several rungs down in a basement, so I didn't quite know these conversations that were going on. But I know that there was interactions going on as the issues came up with how you make polarized beams and what you had to do to modulate polarized beams, for example. That's another example is modulation, how you measure sensitivities to position, angle, and energy. There was a lot of back and forth about how we do that. So I was not directly involved myself, but I know that these interactions were happening in the 80s.
Thank you very much, Krishna.